predictive model that perfectly memorizes historical data is practically useless. If you build an algorithm that curves and contorts to hit every single data point from the past, that rigid structure simply shatters the moment it encounters the unpredictable variations of the future. The mathematical objective of statistical learning is to find the exact level of model flexibility that minimizes mean squared error, or MSE, on new observations. This is a chart showing the Bias-Variance Tradeoff, the governing law of predictive modeling. It graphs model flexibility against test error. Notice the inverse relationship. As we allow a model to become more flexible, bias decreases, because the model can better capture the true underlying pattern. But simultaneously, variance surges upward as the model begins to overreact to random noise in the training data. The optimal predictive model sits at the exact lowest point of the resulting U-shaped mean squared error curve. We can only build a robust model by finding this mathematical trough, and we can only find the trough by measuring our error on data the model hasn't seen yet. To verify predictive accuracy, we require fresh, independent test data. The problem is that real-world data is finite, difficult to gather, and expensive. If we use 100% of our available historical data to train the model, we have exactly 0 independent data left over to evaluate how well it actually works. The solution is resampling. We systematically partition our existing dataset, holding back specific sections to simulate the unseen environments of the future. How we choose to slice this finite data dictates whether our final estimate of the model's error is a mathematical truth or a dangerous statistical illusion. The simplest historical method for handling this is the out-of-sample validation set approach. We take our entire dataset and cut it cleanly into 2 pieces. A common rule of thumb is assigning half the data to training and half to testing, or perhaps a 70-30 split for smaller datasets. This equation shows the sum of squared predicted errors. The model is fitted using purely the blue training chunk, and we calculate its error by measuring its predictions purely against the held-out orange chunk. This approach has 2 structural flaws. First, high variability. The error measurement fluctuates wildly, depending entirely on which specific data points randomly ended up in the training set versus the test set. Second, it consistently overestimates error. Statistical models perform worse when they have fewer examples to learn from. By discarding half our available data just to test the model, we artificially inflate the error rate. The validation set approach is structurally erratic and systematically pessimistic. It cannot reliably locate our optimal model. Leave one out cross-validation, or LOOCV, is the extreme structural correction to this pessimistic bias. Instead of a random split, we slice off exactly 1 observation as the test set. The remaining observations form the training set. This split is repeated n times. The test observation slides down the dataset, line by line, until every point is tested once. By utilizing almost 100% of the available data for training, we completely eliminate the pessimistic bias of the 50-50 split.
And because the algorithm systematically iterates through every single point, there is 0 randomness in the final error estimate. This introduces a massive consequence. If you have a dataset of 10,000 points, you must compute 10,000 completely separate model fits. LOOCV guarantees low bias and total replicability, but it imposes an unbearable computational burden for complex models. There is a major mathematical exception to this bottleneck. For standard linear regression, LOOCV does not actually require you to run n separate model fits. The press statistic provides a shortcut, calculating the exact LOOCV result from a single fit. We find the residual error for each point, dividing it by the complement of the leverage statistic, 1 minus HII, which measures distance from the data center. This weights the calculation. High leverage outliers heavily influence the angle of a regression line. By penalizing them in the formula, we mathematically simulate exactly what the error would be if those influential points had been missing from the training set. For linear regression, this application of leverage perfectly simulates thousands of held-out tests simultaneously, bypassing the computational limit entirely. If LOOCV has minimal bias, zero randomness, and a mathematical shortcut, why is it rarely the standard in modern practice? First, the leverage shortcut only works for least squares. If you train a neural network or a complex tree-based model, LOOCV remains a computational disaster. But the fatal flaw of LOOCV is high variance. Because we only hold out one point at a time, each of our n training sets is almost identical. They share n-2 data points. The resulting predictions are highly correlated with one another, which mathematically inflates the variance of our final error estimate. K-fold cross-validation resolves this. The data is divided cleanly into k-equal chunks, usually 5 or 10. One chunk serves as the test set, while the remaining blocks merge to train the model. Running 5 or 10 model fits drastically reduces computation time compared to 10,000. More importantly, it breaks the extreme overlap between the training sets, driving down the variance of the error estimate. K-fold cross-validation is the pragmatist's architecture. It accepts a tiny increase in bias to permanently resolve LOOCV's crippling variance and compute issues. Resampling is an exercise in pure trade-off management. This chart of the bias-variance trade-off maps our ultimate objective. Leave one out cross-validation sits at the absolute minimum possible bias on this curve, but it suffers from a wider variance spread and massive computing costs. K-fold cross-validation lands directly in the pragmatic sweet spot, balancing computational efficiency with highly stable, low-variance estimates. None of these validation algorithms will output a flawlessly exact decimal of what your error will be in the future. They are cartographic tools designed to map this specific curve, empowering us to definitively lock in the optimal level of model flexibility before we deploy it into the real world.
Every skill mastered was once a mystery. Keep learning, keep improving, and never fear the unknown. If you wish to join me on the path ahead, subscribe.